Now we have our last lecture of Silvia. Thank you so much for being to be here with us.
You're welcome.
For such a short trip. And
it was intense but fun. So, hello everyone. So I heard you have been visiting the accelerator site and the halls, but unluckily for you, you missed the hall B and you missed class 12. And I was actually hoping you would have seen it because a lot of the things I'm going to talk about today are coming from there. I'm biased. That's my experiment. So that's the easiest thing to do for me. So as I showed you for 3 days, a lot of data and results, I thought it would be useful instead of keeping on shooting you more results over to give you an idea of how these measurements are done in practice, because many of you are experimentalists, and I imagine you're going to have to go through data analysis, or you are doing it already. And it can be useful to have an overview of the practical way to get to those beautiful plots that then tell us about the physics we're interested in. So I'm going to give this tutorial or, I don't know, overview of data analysis techniques, and it's geared in particular on the measurement of exclusive reactions, which is what the title of these lectures. So you will see that exclusive reactions are peculiar and they allow you to do cool things. So just an overview here of some of the analysis from which I took inspiration for this tutorial of today. I showed you some of these plots during the lectures before. There are cross-sections and cross-sections differences measured by class 12 for proton DVCS, asymmetries for beam spin asymmetry for neutron DVCS, and different kinds of asymmetries measured by for time-like counter-scattering. I also will refer to cross-section analysis from Hall A for PDVCS and the Rho-zero cross-section analysis by class. So what I'm going to do is to start by the detector, giving you the example of class 12, describe how the detector is made, and then introduce the kind of observables that we are going that we can measure, and decompose the observables in the pieces that you need to extract in order to get the final thing. And then talk about particle identification. I will give some examples of how you can apply machine learning to PID. Very, very kind of elementary examples. I think you're going to have a seminar or a lecture on machine learning or AI afterwards. So there is not going to be any detail about AI itself, just an application of it. And then I'll talk about specific kind of selection cuts, topologies of detection. There was a question yesterday about how we decide how many particles to detect. And so I thought it would be interesting to give some examples on that, and subtractions of backgrounds, extraction of efficiencies, acceptances, and different ways to do, and how we get the systematic uncertainties of our measurement. So this is what you missed today. This is the class 12 detector that is housed in Hall B. As I was saying to Carol earlier, it's the smallest hall and probably the bigger detector. So when you enter, you're kind of, wow, because it's quite impressive. So this is the evolution of the old class detector. The old class detector was kind of a big sphere divided into 6 sectors, while now class 12, after the energy upgrade, is composed by 2 sub-detectors. The central detector that you see here, so the beam comes this way, gets into the central detector. The target is placed in the middle of the central detector, and the scattering products go both in the forward detector, that is this part here, and the recoiling particles at bigger angles go in the central detector. So it's roughly 4 pi acceptance detector, and provides detection of charged and neutral particles over a quite wide solid angle. And the main concept is that it's a spectrometer, so there has to be a magnetic field. In the case of class 12, there are 2 magnets. There is a solenoid magnet here, inside of which several detectors are housed, and this is for the central detector part. And then there is a toroidal magnetic field, for the forward detector, which has 6 coils, and the 6 coils define the 6 azimuthal sectors of the detector, and each sector is equipped with different series of sub-detectors. So I said already the target, the coverage in theta for the forward detector goes from like 5 degrees to 35 degrees, and the central detector from 35 degrees to 100 and something. So there are a lot of different detector subsystems that compose class 12. We have calorimeter, the ECAL and the PCAL that are electromagnetic calorimeter that have the multi-function of providing the trigger, the particle identification, and the detection for neutrals. We have time-of-flight detectors, both in the forward and the central detector, that help us with the PID, particle identification, I'll talk about later. We have drift chambers in the forward detector for the tracking and the determination of the charge and the momentum of charged particles. You have a field, it bends the particle, so by the curvature of the trajectory, you can deduce if the particle was positive or negative. And you have Cherenkov counters for trigger and PID. We have a tracker in the central detector that does the same that the drift chamber do in the forward direction, which is the tracking, determination of the charge and momentum of particles. Then we have the central neutron detector, which is the one I talked about yesterday, that we use for the measurement of neutron DVCS, that is in the central region, and detects neutron. And then there is a detector that is used in particular for the DVCS and GPD experiment that you cannot see because it's buried in here, so I'm showing it here. It's what we call the forward tagger. It's a small detector system that includes a calorimeter, a hodoscope, and a tracker, and it's used mainly to cover the acceptance between 2 and 5 degrees in the forward direction, which is otherwise not covered by class 12. So this is the detector system. Coming to the observables, so I showed you in my previous lectures that we can measure different sort of observables and getting information on GPDs from them. So there are the cross sections, for instance. One thing you see here is the cross section experimentally is defined as a ratio of a yield divided by integrated luminosity, time acceptance, the volume of the kinematic beams in which you are, and then there can be correction factors if something needs to be corrected. So this is a fourfold differential cross-section. It's what I was talking about yesterday. This is to cover the dependence, the kinematic dependence of the GPDs, which is quite complex. If you do, so you see, if you do a cross-section, there are a lot of factors that need to be computed, and it's a quite daunting task to extract it. On the other hand, if you do a spin asymmetry, for instance, the beam spin asymmetry, you're going to take a ratio of the difference over the sum of the cross-section for different values, for instance, of the beam helicity. And this kind of measurement has the advantage over the cross-section measurements that all the factors that you see in the denominator that do not depend on the helicity are going to cancel. So you are going to have, for instance, one thing that it's very complicated to evaluate accurately is the detector efficiency and acceptance. So if you measure an asymmetry, you can avoid that part. So if you have to choose a PhD subject and it says cross-section, run away and go to the one that says asymmetry. No, they are both interesting and challenging, and there can be problems also on asymmetries, but it's just to give you an idea. So yes, here it's how you compute the integrated luminosity. There are a lot of factors that come into place. All this information you can get from the data that were taken with the detector. So the first step, so if you look at here, the first step that you need is the yield of particles, the number of particles that are in your final state. So to do that, there are each detector subsystem as a function to specify it for different kind of particles. So I'm showing here examples of particles that are used in the GPD final states. So we have electrons, protons, pions, and photons, and then there are also neutrals. So for the detection of the electrons in class 12, we combine information from the drift chambers that give us the charge and the momentum of the particle. We combine it with the Cherenkov that give us the particle identification, and the calorimeter that also contributes to the particle identification. And the calorimeter is a sandwich of lead scintillator layers. So it's a sampling calorimeter for which not all the deposited energy is going to be reconstructed. It's around a quarter of the electron energy. It's what we reconstruct. And by looking at the distribution of this fraction of deposited energy that we measure and the momentum that we get from the drift chamber, it's supposed to be at a given value if it's an electron. So by cutting around that value, you can ensure that you're getting electrons. Then if you want to detect charged particles, the typical technique is what we call the beta P technique. So you put together the information that comes from the time of flight scintillator and the drift chamber. The time of flight will give you a measurement of the beta. Beta is given by the distance between the vertex of the interaction and the heat in the time of flight, divided by the time that is also measured by the time of flight. And this is to be compared, is to be plotted as a function of the momentum measured in the drift chambers. So there is this formula, theoretical formula that links the measured momentum to the beta that you would measure if the particle has a given mass. So what you do, you have these lines that represent the theoretical value of the mass that you would get. And then you compare with the beta that is actually measured, you make a cut of a given size, depending on the resolution of your detector, around these bands. And this way you can select the different kind of charged particles. Then photons, as you saw, for DVCS measurements, also for exclusive pi zero measurement, we need to detect photons. For the photons, we detect them in class 12, both in the electromagnetic calorimeter and in the forward tagger. You see here some images that show you the resolution that we obtain with the forward tagger for 2 photons in invariant mass peaking at the pi zero mass. And this is the case of the ECAL, and there is a much better resolution that we get for the forward tagger, about a factor 3 almost better. So the way in practice, we decide it's a neutron, it's a neutral, and it's by checking if there is a match with any track reconstructed in the drift chamber. So this is the first step. You see a hit in a calorimeter, you go back and you see, does this geometrically match to a reconstructed track in the drift chamber? If it doesn't, it has to be a neutral. Then if it's a neutral, you look at the beta that is measured with the timing information. If the beta is close to 1, it has to be a photon, beta equal 1. If it's below 1, it could be a neutron. So this is the strategy that we use to separate charged and neutrals. You check for the matching with the DC. And to separate neutron and photon, you check for the beta distribution. And the cut around beta is going to be determined based on the resolution of the detector. Yes. There is overlap. Yes, so for the kaons, here there is an overlap around 2 GeV, and there are other detectors that are geared for the detection of kaons. That is the REACH, which was not in this image that I showed because it was added afterwards. But the REACH will be specifically the specific goal of the REACH is the one of separating pions and kaons in the region of overlap of the time of flight. But for the other kind of particles that we have, or you can also then try with the kinematic cuts and other sort of things. But it's true that there is an overlap at some point because the resolution of the time of flight is not infinite. Protons, on the other hand, are quite clean in general. So that is good, in particular for the final states that we're looking at. So once you got the PID, you know your particles of the final state. Let's say you have to measure a cross-section. In the cross-section, as you saw here, you're going to have to know very well the acceptance and the efficiency of your detector. So you have to trust your detector well. So one thing that we do to make sure that we select events only in the region of the detectors that are well known is what is called fiducial cuts. So fiducial cuts, the goal is to remove the parts of the detector where the efficiency is not perfect. And also it's not well matched by the simulation, because when you do a cross-section, you're going to use simulation to correct for efficiency and acceptance of the detector. And if there are regions that are at the edges of your sub-detector that are not well reproduced by your Monte Carlo simulation, you're going to correct wrongly the cross-section. So what is done is to cut out regions that are usually corresponding to the edges or to parts of the detector that broke down during the data taking or so on. So I'm showing here some examples of the fiducial cuts that were done for the extraction of the proton DVCS cross-section with plus. So here are the cuts that we do on the different hits that we get in the electromagnetic calorimeter. One thing that is done is to cut the edges of the calorimeter, because if you have a shower produced near the edge, not all of its shower will be contained by the calorimeter if you are too close to the edge. So a fiducial cut means remove the last few centimeters of the calorimeter to ensure that all the showers are contained, are fully contained. And here are an example of cuts done at the drift chamber level. For protons, there are 6 sectors, as I said before, for class 12, and this is the before and then after fiducial cuts. And you see that all the edges where we get all this blue junk, this corresponds to the region where the coils of the toroidal magnetic field is. So there it's outside really the acceptance of the drift chamber. So you remove all that, and then you have a nice clean distribution. You also see that there are some holes that I think these were due to missing time of flight pedals. As you combine the information of the time of flight and the DC, if you look at protons, you will miss events where a piece of detector was broken. So also around here, there are cuts are made in order to ensure a uniform efficiency. Okay, so once we have selected the particle and the fiducial cuts, we have to decide the detector topology. So we are talking about the exclusive reactions. I said exclusive means that the final state has to be fully known, fully determined. So we need to make sure that the particles we detect and the cuts we make tell us which final state it is. And we should do it in principle, trying to minimize the background that we have. But the topology is really correlated on the detector properties, on the final state we want to measure, and the statistic that we have in the data too, and which background channels we have, and so on. So we can have different detection topologies. So I'm showing here, for instance, and I talked about it in the previous days, the measurements that are done for DVCS in all A. You remember the DVCS final state is E, P, gamma, electron, proton, and photon. In all A, they measure only the electron and the photon. They have a high resolution spectrometer for the electron, and then they had a dedicated calorimeter for the photon. So what you can do when you have 2 particles, you can look at the missing particle using what we call the missing mass technique. Basically, you apply energy momentum conservation to deduce the mass and the momentum of the particle that is missing in the final state. And then you look at the distribution of this missing mass. So as you detect electron and gamma, the missing mass is a proton. You have a peak here at the mass of the proton. But you see that having only 2 particles out of 3 in the final state leads to high background. So you then need to find, because there are competing channels that could give you an electron and a photon in the final state. The main one is the production of a pi zero. So if you have E pi zero P, either exclusive or a semi-inclusive production of pi zero, this would contribute to the background here. So then you have to do simulation and other techniques to try to subtract this background. And so one thing that I like to think, I mean, the OLE is provides high statistics experiment, but there are some bigger systematics that come, for instance, from the background subtraction. While on the other hand, in class, when the fact that we can reconstruct the three particles help us reducing more the background contribution. So it's a trade-off. You lose statistics, you gain in background reduction. So in class, both the DVCS and the exclusive pi zero analysis are done with fully exclusive topology, which is detecting electron, photon, and proton, and for the pi zero, the 2 photons of decay. So what you can do, you can build a lot of what we call the exclusivity variable, because you have a kinematically complete final state, and I'll show it in the next slide. And for the rho zero analysis that I showed yesterday, I think, the final state has rho zero decaying in pi plus, pi minus. And in this case, we detected the electron and the 2 positively charged particle, and the missing pion was reconstructed by missing mass, and you can see it here. So there is a clear peak at the pion, and then there is a continuum here, but this part is removed by doing a cut. And if you look at this two-dimensional plot, I find it quite nice. It's correlating the missing mass of the single missing particle, that is the pion, with the missing mass of the EPX final state. So if it's rho zero, there should be a peak around the mass of the rho zero. And then there is also the omega that has the similar mass to the rho zero, but a different decay mode. There is an extra pi zero. And you see how here you see the two regions clearly separated. The omega is here, and the rho zero mass is where the pi minus mass is. So this is a way to ensure exclusivity, and on the other hand, keep as much statistics as possible by only detecting 3 particles out of 4. Here is the case of pi zero reconstruction with class. So what I was talking about, the exclusivity variables, the fact that we have full set of particles detected allow us to build the different sets of variables. We can have the invariant mass of the 2 photons that you see here peaking at the pi zero mass. Various missing masses, you can decide, I look at the missing mass of electron proton, it should give me a pion. I look at electron pion, it should give me a proton, and you see that the peaks are here. One cut that we do a lot in exclusive final states is this coplanarity cut. If you remember, I showed all the observables as a function of pi, that is this angle between the leptonic and the hadronic plane. And this angle can be computed in different ways. You can compute it by using, for the hadronic plane, you can either use pion and proton, or you can use pion and a virtual photon, because the virtual photon belongs to both planes. So you can construct this phi in different ways, but it should be the same phi. So if you compare, make a difference of the 2 phi, you should get a peak, and you see it here, the peak around 0 delta phi, so you cut around it. And these plots show you in green before all the exclusivity cuts are applied, and the red is the final one when all the exclusivity cuts are applied. And you see how little to none background there is outside of the tails, which is not the case for DVCS. For pi zero is much easier because you don't have really competing backgrounds, while for DVCS is much more complicated. So here, coming to DVCS, I'm showing the analysis on deuteron to make the measurement of neutron DVCS. He is falling asleep. I'm sorry. Okay. No, but you can sleep at the end of the week. Just if it's too boring, you can tell me, and I'm sorry if it's boring. Maybe he's a theorist. There you go. Okay, anyway, so this was the example of the neutron DVCS analysis on deuteron. So in this case, what we detect are the active particles of the final state, and we do not detect the spectator because the spectator have low momentum and doesn't make it out of the target or really near near the target. So we cannot detect the spectator, we detect the other particles. So for neutron DVCS is the electron, the neutron, and the photon. And then we build, again, a set of missing masses and missing momentum. And thanks to the fact that the spectator is almost at rest, we can also make the hypothesis that we are hitting directly on a neutron or on a proton and reconstruct the missing mass using the mass of the single nucleon instead of the mass of the deuteron. So this gives us extra variables that we can use to cut. So basically, again, we have the delta phi, missing masses, missing momentum, and so on. So what we do, we look at the distributions of these variables. If they don't show peaks, we maybe use the simulation to help us because, as I said, these reactions have a lot of contamination coming from exclusive pi zero production. So you may first make your plots of exclusivity variable and not see peaks. So what we do, we take the Monte Carlo, see where the Monte Carlo peaks, how big the peaks are, and define the cuts that we can apply. And then we apply them and we reconstruct the final state. Nevertheless, even after you apply the final state, here you see comparison for the E and gamma missing mass squared. The red is the Monte Carlo. Oh, you cannot see it from here, sorry. And the blue or black is the data. So you see that there is it doesn't match still very well even after the cuts. And this is because even after you cut, you're left with some contamination from the pi zeros. So to extract the contamination of the pi zero, I'll get back after it in a little while. So I wanted to now make a little parenthesis about how we can apply some machine learning techniques to data analysis. We have been doing it in particular for the identification of the neutron. Someone, was it you yesterday, who asked me how we detect the neutrons? Yes, and I told you the happy side of the story. We got the signal in the scintillator and so on. But we have to first, as I said before, make sure that there are no tracks in the tracker that match the heat that you get in the neutron detector. However, this has the assumption that the tracker is 100% efficient for charged particles, which is unfortunately not necessarily the case. So what you have some dead regions in the detector due to the way the detector is constructed, or you also just don't have always all the pieces that work of the detector. Some piece broke down during the experiment, or it's really intrinsically not 100% efficient. So you risk to have a hit in your neutron detector that doesn't have a matched track, but actually it was a proton because it was not tracked, this proton. So this is a kind of contamination that you need to find a way to subtract. So what we thought of doing is finding a way to use only the information from the neutron detector to discriminate, to find out if it's a proton or a neutron. So not rely on the tracking. And for this, we used an approach based on machine learning, multivariate algorithms. This is because you will see it after. There are different detector variables that you can use to discriminate between a charged and a neutral. And cutting on each of them separately will make you probably either lose too much signal or not cut enough contamination. So what machine learning allows you to do is to combine all the information from all the variables and try to achieve the best compromise between signal and background reduction. So what we do, but what is cool about, machine learning needs to be trained, no? So that it learns because you give it something to learn on. So you need to be careful in what you choose to train your algorithm. So you need to have a signal that you're sure it's really clean and a background that you're sure it's really fully background. The best thing is to use it from the data than Monte Carlo, because the data in principle is closer to reality because it's the data, so closer than that. So we wanted to get the background from neutron DVCS. So we need to find neutrons that are misidentified. I mean, our neutrons are misidentified as protons. One thing that we noticed when we looked at neutron DVCS is that coplanarity cut that I mentioned earlier, the delta phi cut, had a funny bump on the side here instead of being picked at 0. And we thought about it, and we realized that it was due to the fact that an actual proton hit the detector. We were reconstructing the kinematic assuming it was a neutron. So we assumed a straight track, while instead it had a curved trajectory. So when you reconstruct all the kinematics and do the delta phi, it was coming a bump at the side. So we decided to use this delta phi distribution as a way to realize, are we still having a lot of background, or have we cleaned it up? So what we used is, so for the signal, we needed to have pure, clean neutrons. So to do that, we went to take data taken with a hydrogen target and a final state with electron, neutron, and pi plus. Because in this case, you are sure that you really have one neutron. And we made sure that the neutron was hitting in the region of the central neutron detector. And instead, for the protons, that was cool, actually. We looked at also at EP data, so on proton target, with the final state that was reconstructed as neutron DVCS. But being on a proton target, there could be no neutron DVCS. You cannot make a fully neutral final state if you have a proton target. So these two samples were both coming from the data, and they were used to train the machine learning algorithm. And here you see, so what we use, there are probably more sophisticated methods, I don't know. We are using a package from Root directly to do the machine learning, which is called TMVA, multivariate analysis with a T in front, because Root puts the T in front of everything. So, and you have here the variables of the detector that we use. So this is using only scintillator-based detectors to separate proton and neutrons. And we looked at different quantities, like the energy deposit in the central detector, or the time of flight, how many strips were touched, and other things. And we also included the delta phi that I showed you before, because it's a good variable to discriminate. And as you see, I mean, red and blue, red is background and signal is, red is background and signal is blue. As you see, it's not so clear always how you could put a cut by hand on which, to separate well on each variable. So that's where the machine learning helps, because the machine learning works on event by event basis. And it can tell you this event is more likely to be in the signal sample than the background sample. So, sorry? Yes, so these are the two channels that I said before. The proton, the fake NDVCS using proton data, and then this channel here for the signal, for the neutrons. So this is all based on real data. And here I'm showing what comes out of the training of the it's called a classifier, whatever, of the machine learning tool. So here you have this plot that shows you the response of the machine learning, and in red is the background, and in blue you have the signal. So you see that if you, you have to decide where to cut directly on this variable that is the response of your classifier. And based on that, you can optimize the fraction of signal over background. And we have, here it's cool to see, this is a 2D plot that shows you that delta phi quantity that I said shows a big bump when you have the background far away from 0. And it's plotted as a function of this same response variable. So if you put a cut on this response variable above 0, above here, you see, yes, you see that you are selecting, below 0, it's here. Sorry, there you go, this makes sense. So you are cleaning up all the background that you have. So here it's what is called a ROC curve that is produced by this package that gives you an idea of the rejection factor and the signal efficiency that you have by putting your cut. So you can place your cut along the curve here and optimize depending on whether you want to have purity or efficiency. So if you placed your cut here, let's say you could have 50%, yes, 50% of background rejection, but a lot of efficiency. On the other hand, if you want to reduce the background, you go this way and you are going to reduce your signal efficiency. So you have to find a compromise that is based on the statistics you have, and how much background you can live with, which is something that is difficult to, because at the end, you will still have to find a way to subtract whatever background is left. So the decision to where to place the cut is a delicate one. And we also used machine, yes. I mean, we didn't use an analytic formula to decide the optimization. It's more or less a compromise. We need to see, we try to be as pure as possible, because the NDVCS is a very specific finite state. The background would be the proton DVCS. The proton DVCS has much bigger asymmetry. It's like 25% asymmetry, while the asymmetry for NDVCS is 4 or 5%. So if you have even a small contamination of protons, it's going to give you a fake asymmetry that then you have to find a way to estimate how much it is, how to subtract. So we tried to be more on cutting on the background, to have a cut that removes as much background as possible and lose the signal. It depends. I mean, at the same time, we couldn't lose all the signal because we have very low statistics. So figure of merit, we didn't really define it mathematically. We tried to see as much, cut as much background as possible and see if you still get a decent asymmetry with some error bars that you can live with in the end. It's, yes.
Question: how intensive is the training of your model before?
Sorry, how you can?
How intensive is the training of your model before arriving to the right set of parameters?
Oh, I don't think the training is so long. I mean, you give it to the system, So it's, I haven't done the training myself, because isn't Juan Sebastian here? Where is he? Yeah, tell how long is the training? Because he's doing machine learning for another cool thing, actually. So, and I give you the mic so you can say how long is the training.
Okay, so hello.
He was in the photos yesterday.
So the training, in this case, I think she's using boosted decision
Yes.
trees. The training can take, let's say, 1 minute or 10, depending on the size of the data set.
Yeah.
I mean, for instance, if you have 1 million events for signal and background, it takes like 2 minutes. But if you want to do like neural networks, that can take several hours.
It depends on the algorithm.
Yeah.
Thank you. Those are the people that really do the work. I'm just talking about it. So at my time, there was no machine learning. So, but I learned it. So I'm trying at least. So, okay. So I find this really cool anyway, because I grew up making straight cuts, no? You see a distribution, you cut on it. But then actually we arrived to this after that I put a student in trying to make by hand a cut on all these variables to find, using simulation, how you could optimize this cut. And we found that whatever she would choose, we would have either contamination or lose too much statistics. And I was really reluctant in giving in to machine learning, but then one of our colleagues pushed and said, come on, you are old. You need to look at, no, it's true. I was very, very reluctant. And there are still people that are reluctant because like in the collaboration, we have to have an analysis note approved to publish. And this one, the fact that we have machine learning to separate proton and neutrons is creating a huge stir. I mean, a lot of people want more explanation because they are not familiar with the method. But it's also cool to try new things and to advance a bit. And I mean, if we here stay behind on things like that, we are dead, I think. So we also used it for the time-like quantum scattering analysis, the positron ID, because in time-like quantum scattering, we detect an electron-positron pair, and electron and positrons are identified by the Cherenkov, but the Cherenkov has a threshold that depends on the refraction index of the gas, and that it's at 4.9 GeV, and that after that threshold, you cannot separate pions from electrons. So as TCS needed events also beyond that, we knew there would be a contamination. So by looking at the way the data processing gives you the PID, it tags something as a positron, we figured that there was a strong contamination in the positron sample. The way we understood there was a contamination we took the candidates that were given as positron in the data. We took the ones that were beyond the threshold of the HTCC. We gave them formally the mass of a pion and reconstructed the missing mass of the E plus, which is actually a pion X final state. And we saw a big peak at the neutron mass. So the big peak at the neutron mass comes only if you have a pion in the final state. Again, this was data on proton. So we realized that there is a strong contamination of these events. And so we had to find a way to separate our signal, that is the positrons that are really identified as positron, from the background, that is pi pluses that are identified as positrons. So we use the fact that the particles have different behaviors in the detector. The positron is an electromagnetic shower, produce an electromagnetic shower. The pion is a MIP. And then we looked at different sets of variables from different subdetectors, the sampling fraction that I mentioned before of the calorimeter, and the shape. This is a complicated definition of a variable that defines the shape of the shower. And then, again, here you need to think of what you use to train your algorithm. So for the signal in data, we took electrons from what we call outbanding data taking. We have this torus magnet in class 12 that, depending on the sign of the field, it can either make the electrons go this way, so towards the beam line, or and this is what we call inbanding. And this was the setting of the field used for the main data set. But we can also change the sign and go this way. So in the inbanding, this is complicated, but okay, in the inbanding data set, electrons would go this way and positrons would go this way. So to get the training, we wanted them to make sure that it was a positron-like particle. So we took the electrons going outbanding. So they would go in the same way as a positron. And for the background, we took basically this final state here, where we knew that the missing mass was reconstructed as if the particle called positron was actually a pion. And so at the end, what we got, again, we got our raw curve, and also there you see that we placed a cut where we could have really high signal efficiency in this case, because in this case, the statistic is even worse than the neutron EVCS one. So we had to make a compromise and live with a little bit more background, but that then was subtracted in another way, but have high signal efficiency. So then once you have your final state all nicely selected, you have to bin your data in. And as the Compton form factors, the GPDs depend on many variables, X Bjork and T, and mildly also in Q square. And then you have to get the phi distribution. You need a multidimensional and fine binning to sample all this dependence. And you decided based on how much your statistics available is. So if you have high statistics, you can do a fine binning. And the statistics depend on the cross-section, how many data we took, the beam time, and what's the acceptance, which means what's the topology that you chose. So putting all together, you decide how fine the binning you can do. If you have a very fine binning, it's nicer because the central kinematic of your bin is well defined. If you have to compare your data with theory and you have very big bins, you need to find a way to somehow integrate the model on the big bin, or you'll know that there is in any case an uncertainty linked to the fact that you are integrating over a big kinematics. And I'm showing you some two extremes of what we did. These were the proton DVCS data for class, and here we could do 21 bins in Q square and X, and like 8 or so bins in T, and so it became a huge grid of experimental points. While on the other hand, for the neutron DVCS with class 12, that has a very small cross-section, very small efficiency, and so on, we have only 3 bins per variables. We cannot do it multidimensional. We have to integrate on the other variables, and like bin in Q square, integrate over an X and T, and so on. So this is something that has to be decided based on which measurement you are doing. Then I said that when you do DVCS, you have also the background coming from the pi zeros. In this case, what happens is that you have an EP pi zero event, the pi zero decays in 2 photons, and you're detecting only one of these 2 photons. So it seems a DVCS event, but it can be a pi zero. So the way we do the subtraction, we do it for each kinematic bin, and we are using simulations. So simulations are going to be present in many ways in your life. So to do a simulation, I'm sure you know, you need an event generator. So you need something that with the theory behind, you generate events for your final state. In our case, we had the GPD-based event generator for pi zero. And then you have a package that simulates the detector response. You put through the event of the event generator, you get data that have the same format as your detectors, one like ADCs and TDCs corresponding to the different subsystems, and you reconstruct it with the same package of reconstruction of your detector, and then you look at the response. So the way we do the method to subtract pi zeros, we use the simulation to analyze. The pi zero simulation is analyzed 2 ways. It's analyzed as if it were a DVCS event. So we apply all the exclusivity cuts that I showed before for the DVCS event, get a yield. So this is a yield of fake DVCS event, or you can call them pi zero 1 gamma. So the pi zeros that has escape, and you normalize it by how many pi zero actually are detected as real pi zeros. And then you get the number that you want, that is this one. So how many real how many of your events that you detected as DVCS in the data were actually pi zero by multiplying this ratio here by how many pi zero you actually detected in the data. So these 2 factors are the cross normalization between Monte Carlo and data. And at the end, you subtract this number from the total yield of EP gamma events that you had in the first place. So this is, again, something that requires several aspects. So you are analyzing DVCS, but you also need an event generator for pi zero, which is another channel. So you need 2 event generators, one for your DVCS analysis, one for pi zero. And then you need to do a full analysis of pi zero in the data to get this, this quantity here. So you're actually, whenever you do a DVCS analysis, you do actually 2 analyses because you also have to do the exclusive pi zero 1. So then I'll come to the acceptance and efficiency. This is necessary if you are making a cross-section measurement. As I said before, in asymmetry, everything cancels out. Doing the acceptance and efficiency is quite complicated. And here come in place the fiducial cuts that I talked about earlier, because the fiducial cuts really help you matching things. Look at this. This column is data, and this is Monte Carlo. This is data, and this is Monte Carlo. You see, we have these holes that have been applied both in data and Monte Carlo. If you didn't do that, you would have angular distributions in the Monte Carlo that would not match. I'm showing you this because I went back to look at this analysis and I was amazed by the amount of work that was done, because you really need to go check at the level of wires of the drift chamber, which one was not working correctly, and make sure that your Monte Carlo matches it well. So it's impressive, I think, the final result. And you see it here, see, with these 9 plots are a 1 bin, particular in Q square and X, and each is a T bin, and these are phi distributions. And the red is Monte Carlo, and the data is blue. So once you do that, you can trust your acceptance if you show that your Monte Carlo really reproduces correctly the data. And once you have that, you have a Monte Carlo that faithfully reproduces your data. You define the acceptance as the ratio for each bin of the reconstructed events over the generated events. And you have, again, a huge amount of bin for each kinematic bin of the data. You're going to have 1 value of acceptance with which to correct. And you see the reason why we are doing it in bin by bin is that there is a lot of variation depending on the kinematics on the acceptance. If you would do that integrated, you would really make a huge approximation and error on the evaluation of the final cross-section. So you see average is about 15% for the DVCS acceptance, but there are places where you're covering the edges of phi, places where you have a hole there. So that depends on the detector that is has a very complex geometry. So this is the acceptance, and this is, getting efficiency acceptance with Monte Carlo, but it's not always possible to get good estimates of efficiency acceptance for Monte Carlo. One example is this famous neutron detector that comes back because I love it. The efficiency of neutrons is not so well under control in GEM4, at least at the time. Maybe it's better now, but when I started doing simulations for this detector, you have this thing you can choose in GEM4, that is the physics list, which model you're using to reproduce the interaction of the particles in the medium. And depending on which one I would choose, I was getting different responses when it came to neutrons. Because neutrons are tricky particles. I mean, they are neutrons and they are complicated to detect. So we wanted to make sure we knew really the detection efficiency of our detector. So we used the beam data taken with a hydrogen target, and we used, again, this reaction that we used already for other applications before. EP goes to En pi plus. It's a kinematically complete reaction. And guess what? It's an exclusive reaction. The exclusive reactions are really nice because you can use them for a lot of applications. So we looked at this, and what you do, you construct your efficiency by comparing the number of fully detected En pi plus events, where the neutron goes to your detector here, over the events for which you reconstructed by missing mass the neutron, still ensuring that it's within the geometry. And we got this distribution for our efficiency. So in the region of interest is around 10%, which was the value that I mentioned yesterday. And it's plotted for different angular beams and momentum beams. So we chose this final state because it's fully determined. It has a neutron, and you can reconstruct it both with missing mass technique or with detected neutron. So this, and we did a similar thing to evaluate the proton efficiency in the central detector, because this was an early experiment of class 12, and the efficiency and reconstruction of the central detector was not yet optimized. And to estimate this, we used another exclusive reaction, which is the rho zero electroproduction. In this case, we detect the two decay pions and not, or we do detect the proton. And you construct similarly the efficiency by the ratio of the case in which you detect the proton or it's missing. And then we made the comparison between this efficiency obtained with the data, which is the black points, and with the ones that we had with Monte Carlo, with and without adding some background in it. So you see how there is a sizable efficiency correction that comes from this, about 20%. So I like to say that this is a nice application of exclusive reactions. They not only give us information on proton structure, but we can use them also to verify the performances of the detector and the properties. I'm almost done. So this is a messy slide to talk about systematic uncertainties. So I was wondering on how to define it well, so I went on Google. So basically, systematic uncertainty is a variation in a measurement or a quantity derived from a set of measurements that does not randomly vary from data point to data point. It's systematic. So, and basically the way, the idea here is we have to, you saw there are all these factors that enter in the final state. So for each of them, you make a choice. Let's say you decide that you place 3 sigma cuts on your protons in the time of flight. Or you decide that you cut on given position in a momentum distribution, missing mass, or things like that. Or you choose a certain event generator for your background subtraction or for your acceptance and so on. So each of these choices brings with it a systematic uncertainty, because you could have done another choice and maybe you would have had a slightly different result. So what all of you have to do at the end of the analysis is this. That is the most painful, I think, part of doing an analysis, because the only way, at least the way we do, to test the systematic is making different choices and getting again all the results. So that is quite painful, because I'm showing you here the example of the cross-section analysis for class for PDVCS, and this is the difference of cross-section. Basically, what we have here are different values of sigma. You don't see it on the X, from 2.5 sigma to 3.5 sigma in some exclusivity cuts. Okay, sigma is the width of the Gaussian distribution that you had. And basically what we did is making like 10 variations to make it bigger and smaller, this cut. And every time you verify how much is the cross-section. So you have to redo 10 times all your analysis for each variation. And after that, you fit it with a straight line and you get the half of the last to first bin variation, and then you get that difference as your systematic uncertainty. And this you do for each of the decisions that you made before. So you may have to do something like 50 versions of the same analysis or something like. See here, so you have to redo it, the analysis over and over. And I'm showing you here for one bin of the cross-section, there were something like, 7 different sources of systematic uncertainty. Each of them implied something like this to be done. So 7 times 10, 70 times the analysis. Of course, you don't do it by hand. You have a code that does it. But keeping track, it's not easy. So in the end, when you have all this, you do it bin by bin, and then you can combine all the sources of systematic in a quadratic sum. And so I'm coming to the end. So just a global summary of the whole thing is that exclusive reactions are great to explore the structure of the nucleon, and we can get information via generalized Parton distribution. And about this last lecture, measuring cross-sections and asymmetries for this kind of reactions is challenging because they have small cross-section. We need to get our observables as a function of many kinematic variables. The final state has many particles, so there is a problem of detection efficiency that is limited, and also you need to know the efficiency for each particle very well. And there are also various kinds of backgrounds that need to be accounted for. So a detector like class 12 that is multipurpose and large acceptance is ideal for these measurements, but getting the measurements out is not trivial. So there are several analysis techniques that can be used for the extraction of the observables, and I think it's fun to think about new ways, and I hope I showed you that there is space to have fun and to be creative also in analysis of data. And I would like to thank you all for being here for these lectures. It was really fun to be here, and I hope everything goes well for your life and for your future. Thank you.
Okay.
1 hour.
Yeah. I think we have a few minutes for questions.
Yes. Ah, you mean to simulate?
Yeah. Because if you have part of the shower, part of the energy being deposited at the edge, right? I guess it might be possible to.
You would like to recover whatever we cut because we don't measure it all. Well, why not in principle? You need to be sure of what particle it is, the one that you send to the edge before you train. Maybe for that you could train with Monte Carlo. That could be something to, but okay, that is if you are starving for statistics in those regions in particular, but yeah. Yeah, that. But,
so then wouldn't it like correlate those with maybe accidentals in the central?
No, the energy of the shower should, what we have at the edge is in phi. So in phi, there shouldn't be too much variation of the energy of the shower. Yes, the segmentation is in phi. The sectors of class are all defined in phi. So there shouldn't be really energy-related decrease. It's really a geometric thing. You are at the edge, you don't reconstruct the whole shape of the shower. But yeah, that's interesting. You need to start thinking of using machine learning in anything. I mean, we are now using it. No, it's true. It's Alberto, maybe you think it's silly, but I think nowadays to be in the business or whichever business, you need to use it. It looks cool. It's going to be looking good on your CV. And now we are using it in particle reconstruction. So we are using it to clean up background in the drift chambers for the tracking. It's applied even not in the analysis, but at the level of data reconstruction in the software. So it's useful. I mean,
You get 6 hours of that on the third week. So.
there you go. Exactly. No, mine was just, I just showed them a couple of applications. So, yes. Oh, today I missed you.
Just to add to that, I think there are actual experiments because I'm part of a Phoenix collaboration. They do look at the showers and based on it, I think it's graph neural network or whatever they call it in part of machine learning, where they can do machine learning to based on the shape of the showers or something like distinguishing. That's been actually done in different experiments. There you go.
Very nice idea. Yes.
This is today we went to see the.
Oh, yeah.
So I think the first was Hall D that we saw, and that was the photon of this target. And
yes.
the experiment was like cylindrical. And
It's a solenoid.
Yeah, and that was interesting because most of the collider experiments in the solenoid, like the cylindrical kind of.
That's why you should have seen class 12. It's
Yes,
a
I saw,
toroidal.
yeah. So the explanation that he gave was like even though it's a fixed target experiment in Hall D, because of the energies that are involved are smaller, they wanted more the acceptance in this. Is that the same reason here too?
Here we have this geometry the geometry having the forward detector, and the central one is because the majority of the particles are going to go ahead because of the boost of the beam, and the central is just added for the recoil particles. But the geometry was, I mean, the concept of the toroidal magnet and the 6 coils and so on was already part of the old class. So it's a development of a detector that existed for 15 years before. But I think it works pretty well for the purposes that we have to work for. Sorry, am I taking too long? You are looking. No, you are looking at me. Okay. Yeah, no, I'll be fine for the flight. Anything else? Okay.
No,
Thank you so much. This was fun.